He has joined. Okay, we can start up after 15 minutes. Good evening, Prashant. It seems nobody else has joined today. We'll start after a couple of minutes. Okay, so how are you, Prashant? Have you gone through the last day's recorded lectures? We can start, I think. Let me share my screen. Uh, all right. What is it? Hmm. Okay, so as nobody is joining today, we will try to finish today early. Uh, and if you have any doubt, Prashant, you can ask because it is just one-on-one interaction between you and me. So I am Sutam Sadhukan. I am a teaching assistant and PMRA research student at IIT Bombay. I welcome you to the fifth weekly interactive session of NPTEL course code C39, which is water and wastewater treatment, instructed by Dr. Bhanu Prakash Bhelanki, who is a civil engineer from IIT Roorkee. Mm. So today is the last day of the month of February, and with this session, all the 5 sessions are covered. So last class we actually did complete the BOD problems. If any doubt regarding BOD, and all the relevant problems, then you can ask. Otherwise, actually, we have finished that, but I thought that still certain concepts are left over from BOD. I mean, if some problems are given in a complicated manner, then it might be uh, a problematic for you to solve. So that's why I thought to discuss a couple of more BOD problems. One is very common, the first one. Students who answered it in the last class, I mean, they did it correctly. So let's see. We'll just practice once again. So the first problem is a municipal wastewater treatment plant receives a flow of 25 megaliters per day or million liters per day. The average BOD is 235 milligram per liter. The volume of the treatment reactor is 5000 meter cube and the microorganism concentration is 2.5 gram per liter. Hope I am audible and my screen is visible well. Yes. Now, if the reactor is operated at a hydraulic retention time of 12 hours, then you have to find the daily food by microbes ratio. So I don't remember who was the guy who gave, I mean, correct. Similar problem was given where the concept of F by M ratio required in the last class. This is also similar problem. So you can try to solve it and give me the answer. I will wait for 4 or 5 minutes, let's say. Food by M ratio. I hope you are able to. I don't remember whether you were the guy who solved it correctly or not in the last class. So this similar problem, just for practice, you can solve and give me the answer because the ratio is important uh, from activated sludge process water treatment point of view. That's why we solved 3 problems. One was based on monode kinetics, another one based on not no, it was not a problem. I think it was just an MCQ, conceptual MCQ. One was based on the balance between the food, that is the BOD consumed, and the amount of microbes generated, and they are linked with the help of the yield coefficient and the death coefficient of the microreactor. One problem was based on that, and yes, F by M ratio, I think you have given it correctly. So you can calculate S into hydraulic retention time. S is your it is the BOD, right? Yeah. And V into H. V is the volume. Yes, yes. I think you have given the formula correctly. So let's solve. So the useful data that is given are flow rate Q equals to 25 megaliters per day. That is equals to 25,000 kiloliters per day because 1 million equals to 1000 kilo. Then BOD that is coming in, it is S0, S not equals to 235 milligram per liter equals to 235 gram per kiloliter. These two are same units, milligram per liter equals to gram per kiloliter only. Then reactor volume V equals to 5000 cubic meter, which is 5000 kiloliters, and ml/VSS, that is the microbial concentration, which is termed as the mixed liquor volatile suspended solids. It is X equals to 2.5 gram per liter, that is 2500 gram per kiloliters. So all are in kiloliters unit, right? So the HYD, I think you meant it to be flow rate, right? Because the retention time here, it is an unnecessary data. So that's why useful data given, it is written as the useful data given. Otherwise, all the data will not required here for calculating the food by F by M ratio. So HYD, I don't know what you meant by that. If it is the retention time, then I don't think it is correct. It must be the volumetric flow rate. Okay. So now the solution goes like this. So the daily ratio F by M, it is given as Q into S naught, that is gram per day, divided by V into X, that is gram. So gram per day divided by gram, that means per day, F by M per day. So which becomes as Q is 25,000 basically into S naught, that is 235, divided by under first bracket V into X, that is reactor volume 5,000 kiloliter divided by X, that is 2,500 gram per kiloliter, which becomes 0.47. Okay. So now we'll move on to our next problem. Uh, where you have to determine the effluent BOD in milligram per liter or gram per kiloliter of wastewater with a flow, that is Q, of 10 million liters per day, and the following design conditions. So design conditions are given as an unit is given at the right hand side, right hand column. So there is one tank, the flow is 10 mld, as stated earlier. Influent BOD is your 95 milligram per liter. You have to calculate the effluent BOD. This BOD is S naught, that is the incoming BOD. Influent TSS, it is 70 milligram per liter. First order death rate constant, that is KD, is 0.05 per day. That is per day. It is the rate of the death of the bacteria or microbes that is treating the BOD. Specific yield Y is 0.5 milligram of VSS, that is volatile suspended solid, per milligram of BOD5 removed. So the influent BOD that is coming in, it is essentially BOD5 only, but all the data that is given here, they may not be required for solving the problem. And then mu m is given as 2.5 per day, Ks is given as 150 milligram per liter, and sludge H, or cell retention time, or solids retention time, whichever you may say, that is theta c equals to 8 days. So you have to calculate the S. S naught is given 95 milligram per liter. It is the influent BOD. You have to calculate the S, which is the effluent BOD. Consider the tank to be a mixed flow reactor or continuous star tank reactor, CSTR or MFR, or continuous mixed flow reactor, CMFR, whichever you may like. You may consider that. So that means whatever BOD that is present inside the tank, that will be equals to the effluent BOD. So S in equals S inside the equals to the S effluent that is going out. But S naught, the influent BOD, is essentially different. But you have to first identify from mass balance which data are required and which are not. I'll wait for 2 to 3 minutes. This is a mass balance problem essentially. If you just remember the formula, just looking at the, or if you are having the SATS notes with you, or if you are opening any tab where Sir has explained this in his lecture, then you can directly use the formula from his lecture. Otherwise, I will anyways derive the formula for you. Not in this class. I think in the next class. Let's see what I actually expected more people. So I thought if they required, then I would uh, derive the formula. Otherwise, I in this class I'll just use the formula directly. So what about you, Prashant? Do you remember it, or I mean, or should I derive it in the next class? What is your opinion? Okay, so in the next class I will explain the formula, but in this class I will just use the formula for solving the problem. Okay, so the solution goes like this. First, the useful data given is the concentration at which half of the maximum growth rate देखने को मिलता है. That means the it is the constant. It is a constant which is defined as the concentration at which half of the maximum growth rate is observed. So it is Ks equals to 115 milligram per liter. It is given in the question. I hope you have written this data table. So you will see that certain parameters will not matter at all. Okay. Now, the first order death rate constant, that is Kd, is given as 0.05 per day. How did I understand it is first order? Because in the problem it is only given as Kd, right? So can you answer? By seeing the unit. So it is per day. That's why this is how it is understood. Okay. So now sludge age, considering monode kinetics. How I and considering monode kinetics here. If you see the data, so can you say that why am I considering monode kinetics here? Okay. So you can see here it is given as mu m. So the mu m, the value is utilized is monode equation. So as it is given, so that's why I am considering monode kinetics here for the growth of cell. Growth of cell means the microbial cells, right? Okay. So the sludge age considering monode kinetics is 8 days. Now the maximum microbial growth rate as it is given in the question is mu m equals to 2.5 per day. So now based on these four data only, the solution we will get. You can see that in the problem, most of the data, that is influent BOD, influent TSS, specific yield, all the data are not required. Right. Number of tanks is obviously required. I mean, if it is 2, then multiplied by 2 like that way. But all the other data, as I told, they are not required at all for the calculation of effluent BOD. So this is the formula for the calculation of effluent BOD. Where effluent BOD S is the concentration of the that is the differential concentration of dissolved oxygen that is present inside the tank and also coming out. The influent BOD is not required for calculating S. You cannot see any S not term at the right hand side of the formula, right? Okay. So hence S equals to, you can just put the all the values 115 into 1 plus Kd is 0.05 into theta c means 8 days whole divided by cell retention time. This is 8. Again, this is the difference between mu m and Kd, that is 2.5 minus 0.05, that is 2.45 into 8 minus 1. So if you calculate this, it will come out to be 8.656 milligram per liter. So you may be thinking, if you have watched the lecture, then okay, but if you have not watched, then you may be thinking that how this formula for effluent BOD came into the picture, but not even the internal BOD, the BOD that is coming in, that is not even considered. So in our last class, we discussed about monode kinetics. What is the formula for monode kinetics? Can you say, Roshan? You can type like uh, yes. In my YouTube channel, all the yes, right. So yes, so this is 1 by mu. So if you consider it as mu, then it will be mu m into s divided by ks plus s. So okay, in my last class, I actually in my YouTube channel also the video is uploaded. So there you can have a look that we discussed the equation for monode kinetics. We discussed the equation of the sludge and not sludge, the generation of sludge as compared to the BOD consumed. So we made a balance, and we used the term yield in that balance equation. So it was something here you are getting the value of s. In that equation you are getting the value of x, that is the biomass that is present at a certain time. So if you just take that equation from that formula, and you also take that monode equation, and you put the mu value, that is mu max into whatever you have written, you just put that value in that equation, then you will get the formula for the effluent BOD. So if I think I actually expected more people to come, and whether if they require, then I will explain the formula in my next class. Actually, I will derive the formula. So okay, as nobody has come, I'll assume that I have to redo it again. So I have not done the derivation, but the separate formulas I have discussed. Just these two mass balance you have to do together. Then only the formula for the effluent BOD will come into the picture. I will, in the next class, I will actually derive the formula. Okay. For the time being, just up to the just you have just to remember this, and you just put the values here, or otherwise I will, for those also who will be watching the recording later, I'll give it as a homework. So you just try yourself. I will anyways derive this in the next class if nobody has done it. But if you have done in your home, then you can watch the in my next class, and you can just compare whether you have done it correctly or not. Okay, so if you have done correctly, then this formula will come anyways. So there is no correct or incorrect. So the steps may be different uh, of you than mine. Okay, so let's recap what we did in the last second half of our last class. So first, we solved a problem, right? The problem was based on the length of what? For the removal of discrete suspended particles. So the idea of particle settling came into the picture, and we solved certain problems for that, where the surface area of the settling tank is required, but the depth of the settling tank was not required. Though it may vary depending on the, I told that depending on the frequency of the opening gate of the sludge, of the solids that is getting deposited at the bottom of the settling tank. But the surface area, where length into breadth is important, depth is not taken into account. So though the depth is was in the question, so it didn't came in under the useful data, and based on that you just calculated the length of the tank. It was one problem, and in another problem we solved a channel type grid. I mean, we solved we also required certain length only here. Oh no, not a length. So here we required the maximum diameter of the particle that can effectively be removed with 100% efficiency inside the channel type grid chamber, which has a length of 10 meter long already given. So this problem also is solved. So if Prashant has attended that class, then it's okay. If you have attended online lecture and if you are having any doubt, then you can ask for these two problems. I will not be discuss. Otherwise, I will not be discussing. These are just recaps of the last class. So I will not be discussing in detail. So you can watch the recording, and in later classes also you can come with questions if you are having doubt. Okay. So we actually took the length, the flow rate, the breadth of the tank. Okay. And then we got the settling velocity as the total flow rate divided by the total surface area, which came out to be the sorry, yes. So which came out to be 0.025 meter per second. So it is based on this overflow rate, that is Q, this volumetric flow rate into this surface area. So that will be your settling velocity of the particle. Okay. So that's why Vs may be equated with this formula that I promised the students to derive in this class, because this is a very important. So the BOD one that I discussed earlier, that you can try in your within this week. And if you have not, have you tried to derive this formula? In my last class, I told that I asked people to try how this is coming to do a force balance and get this formula. So have you tried this? You can see that in this question, it is mentioned as Stokes law, assuming Stokes law applied. Okay. So the formula that you are getting here, it is based on the Stokes law. Stokes law regime. Have you tried, Prashant? Uh, okay. So I'll be deriving it in this class. So in that formula, we put the value of Vs, and we in this way we got the d square, which is given in the which is asked in the question. That is nothing but the diameter of the particle that will be effectively settled. Okay. So how did we came up into this formula that we'll discuss today? So the derivation part, right? So as I showed the question there, the Stokes law region is mentioned, or assuming Stokes law. Stokes law means what? The particle's Reynolds number, which is given as REP, that is approximately equals to 1, or it will be a one digit number to be said specifically. Mostly it will be yes, drag force and gravitational force, definitely. So that balance actually we will be doing in this class. Okay. Yes. So if you have tried it, then it's okay. Otherwise, for the recording purpose, I will just tell it. Okay. So definitely we have to do a force balance between the gravitational force and the drag force, as you have said, and also you have to consider the buoyancy. So you all have studied in your school level the Archimedes principle of buoyancy, right? So if the particle is submerged inside a fluid, that fluid may be gas, that fluid may be liquid. What happens then? If it is partially or fully submerged, depending on the fraction of the volume of the submerged particle, uh, uh, an equal amount of volume, actually an equal amount of volume, yes, fluid is displaced. Okay, so the fluid amount of fluid that is displaced by the partially or fully submerged particle, it has got a certain volume, same as the submerged fraction of the particle, and that volume of fluid, be it a gas or be it a liquid, has got certain amount of weight, right? So that volume into that weight, that will be the amount of buoyancy force which will be exerted on this particle in the opposite direction of the gravitational force. In whenever the particle is in air, that is in the gaseous fluid, in that situation the buoyancy force is not much, it can be neglected. But when it is submerged in the liquid, then depending the volume of submersion, we have to consider the buoyancy force for the force balance equation. Okay, for deriving the formula that was required in the earlier problem. So now, as we can see, the buoyancy force and the drag force is acting in the upward direction, and the gravitational force is acting in the downward direction. So that's why, so in the left hand side of the equation, we have written as buoyancy force plus drag force, and in the right hand side of the equation, we have written weight of the spherical particle. Okay. So now, the buoyancy force we have written as B, and drag force we have written as FD, equals to the weight of the spherical particle we have written as W. W means what? W means mass into gravitational acceleration, that is W equals to mg, equals to G remains as it is. M means the volume of the entire particle, that is the particle volume, into the density of the particle, that is the particle density. Is it clear till now? Now, uh, to determine the buoyancy, we have to do something like this. So first we have to determine the fraction of the volume of the particle that is immersed. Okay, so in our case, we are separating the particle from the water by settling, right? So that's why, because it is a water treatment, and we are separating the particles, the bigger size particles which are having diameter more than 10 to the power minus 5 meter, so they cannot be suspended or they cannot be dissolved. So that's why they are floating. We are just separating them out. So in general, so there are also certain particles which have got bigger size, but they can be dissolved, which are got smaller, even that they can not be dissolved. There are exceptions, but the general size of the particle that we discussed in few classes back, it is between 10 to the power minus 5 to 10 to the power minus 7. It is the transition region, it is the colloidal or suspension region. Smaller than that, that is 10 to the power minus 8 and onwards, they are dissolved, and 10 to the power minus 5 meter, and above that they are actually floated. So they are floated means they are not mixed. If they are heavy, they will not be floated, they will be submerged. So here we are considering that the particle is completely submerged. So that's why the immersed volume will be equals to the entire volume of the particle. It will not be a fraction of the. Otherwise, if the fraction is x, it will be equals to x into v. So here it will be entirely v. Okay, into the density of the fluid, the particle, the volume of the dispersed fluid will be equals to the submerged volume of the entire particle. Okay, so that's why we are multiplying it with the fluid density into G, that is the weight of the displaced volume of liquid. Okay, so this gives you the value of the buoyancy force. plus, as I told, for Stokes law region, the formula of FD, that is the drag force, is something like this: 6 pi mu r into Vs. Vs is the settling velocity which you require. Okay, so this all was also there in your plus 2 level, that is 10th, 11 and 12th level. If you had science, then this formula was there. Now this equals to the weight of the spherical particle. What is weight? So the particle density I have considered as rho p. Okay, rho into g. It is, I think it is clear. Now particle volume, as we have assumed it to be a spherical particle, then it will be 4/3 pi r cube, where r is the radius of the particle, which is equals to half of the diameter. So now the immersed volume of the uh, particle will be same as the entire particle, as we are considering complete immersion here. So that's why it will all the immersed volume will also be 4/3 pi r cube into rho of W. Here we are considering water, so that's why the fluid is liquid water here. Its density we are considering as rho W into G. G is the gravitational acceleration plus 6 pi eta r V, as usual, equals to this one. So now to simplify, we are dividing the both sides with pi r by 3. Okay, so if you divide it with pi r by 3, r goes out, so it becomes 4r squared into rho W into G, plus here you divide by with pi r by 3, this gets cancelled out, and the 3 goes up, and this becomes 18 mu into Vs, which equals to, here also you multiply it with pi r by 3, sorry, divide by pi r by 3, and it becomes 4r squared into rho p into G. So is it clear till now? Okay. So if you have any doubt, you just unmute and speak. So the next step is we are taking this portion to the right hand side, and the sign changes into negative. So 18 mu Vs, this becomes equals to 4r squared into rho particle into G minus 4r squared into rho water into G. From where we take common the 4r squared term and G term. So this both we take common, 4r squared G, and within bracket rho P minus rho W, which is the density difference of the particle and the water. That actually remains within the bracket. So this is equals to the 18 mu Vs. Simplifying further, we take the 18 mu at the right hand side, which becomes, sorry, here it will be something like divided by 18 mu will be there. Right. So I hope it is clear till now. If you have any doubt, you can just ask. Okay. So after this portion, uh, we just taken the 2r square. I mean 2r square means 4r square, which is nothing but your d square, because diameter equals to 2 into radius of the particle, and we have taken the rho W, that is the density of the water, common from the bracket. So within the bracket, which became as rho P divided by rho W minus 1. So you get it till now? Okay. So now, is it? Yes. Hmm. So now the ratio of rho P by rho W, it is the density ratio of the particle divided by the density of the water. It is the ratio between two densities, which is nothing but the specific gravity. Specific gravity is the density ratio of the particle and the water, and it is a dimensionless parameter. Okay, so now the formula upon further simplification became Vs equals to rho into G whole into capital G minus 1 into d square divided by 18 mu. This is how we arrived at the formula. Mu is the uh, viscosity. Viscosity means the ability of the fluid to prevent the flow of any particle inside that fluid. So the drag force actually basically comes from the viscosity. Okay, and see if the fluid liquid is very sticky, let's say honey, then the viscosity will be very high. But if the or heavy oil, then the viscosity will be very high. If it is very light oil, water or milk, for those viscosities are low. That's how you can get a feel of it. Okay, and this G is gravitational acceleration, this G is specific gravity. So this is clear. We just kept rho W as rho only because the other rho is gone. That's why. Okay, so hope it is clear till now. So this rho is density of the fluid. This mu is also viscosity of the fluid. This G only is the specific gravity of the particles. So I hope while solving the problem, you won't confused that which one is of which one. So maybe in the problem, they may give density and viscosity of both the particle and the liquid, and you may get confused which one to use in the formula. So it is important to remember. And Vs is the settling velocity of the particle. Okay, this is of the particle, G is of the particle, Vs is the settling velocity of the particle through the fluid, having density rho and viscosity mu. D is the diameter of what? They may say that there is a channel of diameter something. No, D is the diameter of the particle. It is dp. So that's this is important while calculating the calculating the settling velocity. So this is what of what that you have to remember. Okay. So this is for assuming the Stokes law region where Reynolds number is 1 digit. Okay, Reynolds number of particles. So now certain other complicated thing will come into the picture that I will say. So as we have started a bit late today, we will not be taking any uh, uh, break. Okay, so is that fine for you? If you need break, you just tell me. Otherwise, I'll just continue. Okay. So yes means what? I can continue, right? Okay. So otherwise, you can take 2 minutes break. No issues for that. So if you have ever opened your tap water, you will see when the tap is running at a very uh, what can I say? You are not fully opening it. It is running. Um, I mean, it is running at a very slow rate. Then you will see that the water is falling very slowly, and you can. It is a transparent kind of thing. The other side, if you look at the flow stream, if you look at the flow stream, you can see the background through the flow stream, right? And if you just increase the velocity, then what will happen? It वो जो flow rate flow जो आ रहा है ना फट जाए. That means you will not be able to see the other side of the flow. So this phenomena and this phenomena. So in the right hand side, whatever you see, it is defined as the Stokes law region, where the Reynolds number or Re, that is a 1-digit number. In case of particle, not always, that we will also see. We are actually assuming the laminar flow region for deriving the formula. Now, the Reynolds number, what is this Reynolds number basically? It is a dimensionless parameter which is given by the formula dv rho by mu. Okay. Now the rho is the fluid density, mu is the fluid viscosity. If you take the ratio of the two, that is mu by rho, then it comes out to be nu. So nu equals to mu by rho, which is defined as the kinematic viscosity or momentum diffusivity. Okay. So Re equals to dV rho by mu becomes dV by nu. Hope it is clear till this point. So the mu, which is simple viscosity, it is sometimes called as the uh, dynamic viscosity. Okay, its unit is Newton second per meter square. It's SI unit. If you divide it with the help with the rho, that is the density, then it becomes at from dynamic it becomes kinematic viscosity or momentum diffusivity. Its unit is meter square per second. Meter per second square is the unit for g or gravitational acceleration. It is the its unit is meter square per second. Okay. Okay. So now for turbulent condition, the Reynolds number is very high than 1. So once you increase the velocity, it becomes like this. So this is the Reynolds number, right? So you can see Reynolds number is directly proportional to V. This V is the velocity. So as you increase the flow rate, velocity increases. That's why Reynolds number also increases. And you can see the difference here. Here Reynolds number is 1-digit Reynolds number. Here Reynolds number is far more than. Okay. So that's why actually if you plot the particles Reynolds number, whenever the Reynolds number is in 1 digit, then you will see laminar flow. If it is a 2-digit Reynolds number from 10 to 100, 10 to 99, then around this region it is a transient flow. And from 100 to above, 100 above anything, so it becomes a turbulent flow. So what is transient? It is a transient transition region. That means the way the flow rate changes from the laminar flow to the turbulent flow, it is not a sudden change. There is a transition region for the flow to become fully turbulent starting from laminar. So this region is this region where the particles Reynolds number lies between 10 and 100. That is 10 to 99 around that region. Whenever the Reynolds number is in 2-digit, you remember it to be transient flow. Whenever Reynolds number is 1-digit, it is a laminar flow. When Reynolds number is 3-digit or 4-digit or 5-digit or more, they are turbulent flow. Where eddies occur. What is eddies? So if you consider there is a still water, right, and the particle is falling through the water or through any kind of fluid. So if the velocity of the particle is very slow, then these are the streamlines of the other liquids. So this is how the particle will come down. If the velocity of the particle going through the fluid is very high, then in the back region of the particle, so whenever the particle will be falling through the liquid in a very high velocity, the eddy currents will occur at the back of the particle. So the streamlines, those are there in case of the laminar region. Whenever the velocity is very low, that means the Reynolds number is very low. In that case, uh, the drag force that is offered on the particle by the liquid will be very low, which is given as by this equation 6 pi mu r into v or 3 pi mu into d into v. But whenever it is in this eddy region, that is in the turbulent region or in the transient region also, whenever it is transiting from the laminar to the turbulent flow, in this region also, the drag force will be more than the value for the which is given for the Stokes law region. Okay. Here I would like to mention one thing. The particles Reynolds number and normal Reynolds number, there is one difference. Particles Reynolds number considered velocity of the particle, diameter of the particle only. The nu is always of the liquid. But whenever there is a channel, let's say there is a circular channel of circular diameter, cylindrical channel, closed channel, then the diameter will be the diameter of the channel only. If there is no particle at all, the velocity will be the velocity of the fluid only, flow rate divided by cross sectional area. Whenever the channel is open, then the diameter will be the weighted diameter. Some certain other things will come. So the range that you see here, that I told you earlier, so this laminar flow, that is your if it is one digit, it is laminar. If it is two digit, it is turbulent. If it is three and more digits, then it is turbulent. So this is true for particles Reynolds number only. REP equals to dP into Vp by nu. If it is not a particles Reynolds number, then the number that I told earlier, the Reynolds range of Reynolds number will be different. If it is an open channel flow, then the range of Reynolds number will be different. If the particle is not spherical, is very complicated, certain other things in nature, then the number also may get different. So this is essentially the spherical particles Reynolds number for our problem only. If the geometry of the channel, geometry of the particle changes, then also it may vary. Okay, so the one digit, two digit, this funda may vary. Okay, so this number range is for the particles number only, not for channel or not for open channel flow, open or closed channel or conduit or nothing of them. Though the Reynolds number formula remains the same, but our focus is the particles number, not the normal Reynolds number. That I hope this point is clear, because this concept is very important. The many other data, many other excess data may be given in the question. So which diameter to take, which velocity to take. If flow rate of the fluid is given and the channel diameter is given, and you are talking about the settling velocity of the particle, then you have to focus on the particles number, not the entire diameter of the channel or whatsoever. Okay, so I hope it is clear. So now for our earlier problem, it was mentioned that it was in the Stokes law region. If we just calculate the Reynolds number of particles number of our earlier problem, then we will get something like this. So the diameter of the particle is this many millimeter. The velocity of the particle is this many meter per second. The nu, that is your momentum diffusivity, becomes rho by mu by rho. So mu is this and rho is this. So after simplification, all the numerator and the denominator units are meter square per second. And if you take the ratio, it becomes 4.4, which is a dimensionless number and which is a one digit number. That's why it is laminar. So that's why in our earlier problem, it was told that assume Stokes law region. If nothing is told in the question that you assume Stokes law region, then you have to start by equating FD equals to this only. That is the formula we derived earlier. You have to use this formula only. But later you have to do iteration. Later you have to check that whether RE that came out of this equation. So because in this equation VS will come out, and this VS you will put while calculating REP, and you have to check whether this REP is in one digit or not. If it is not coming in one digit, then this VS that you have calculated, that is not true if this Stokes law region is not mentioned. If it is mentioned, then it is true. So we'll be solving one. You may be confusing now. I don't know. So to get a more clarity, we'll actually see one more problem, which is a bit complicated than the earlier problem. So that we'll see. So I hope any doubt till now you can ask. There is a concept in fluid mechanics that is called as boundary layer. So if there is a particle and it is falling through the liquid, so you will see that the streamlines are getting contracted, right? But if you go at a very longer distance from the surface of the particle, you will see streamlines are intact. So they are not getting affected by the solid wall. So the distance up to which the fluid layers get affected by the presence of the solid layer, that distance actually is called as the boundary layer thickness. So this will not be required, just for your information. In case of AD, you can see that this is up to this region it is getting affected. So from the center point up to this point, it is called as the boundary layer thickness, and that means as the particle is moving through the liquid, or it may so happen the particle is stationary, the liquid is moving past through the particle. In that situation, what will happen? Same scenario will happen. So the particle wall will affect the liquid layers. Okay, so that means there is a motion either of the fluid or of the particle. So there is a relative motion, right, between the surface of the particle and the fluid layer. So there is a relative motion. Because of the relative motion, you can see there is an effect uh, on the layer of the fluid or layer of the liquid. Okay, so this layer is because of what? This layer is this effect is because of the motion only. So motion means what? It has got a mass. It is having a velocity. So mass into velocity is momentum. So the momentum, as if it is getting diffused from the surface to the inner layers. So that's why the new it is called as the momentum diffusivity. Momentum it is getting diffused up to the boundary layer thickness. Okay, so I hope the concept is clear till now. Okay, so we will solve a bit complicated problem. So one thing I just mentioned. So you can see that in this case, whenever it will be a turbulent flow. So in normal flow, it will have a certain terminal settling velocity, right? But in this case, the drag force will be more than whatever the value is for our Stokes law region. Okay, so that's why the terminal settling velocity for Stokes law region, whatever it will be, the terminal settling velocity for the turbulent flow region or the transition region will be lesser than the terminal settling velocity of the laminar flow. So that will how we will see in the formula. So we earlier we just derived one formula using this thing, right? So here RE was one digit and Stokes law was valid, but here RE is more than one and Stokes law is invalid. So here, if we do the balance, same balance up to this level. So after this level, what will happen? The weight of the particle will remain the same. The buoyancy force will remain the same. But as I told earlier, that FD value will be more than this value. So we have considered a plus delta, which is a positive value. Something positive will be there. So that we have assumed. The Stokes law drag force plus some other positive terminology depending on how much it is deviating from the Stokes law region. Okay, so it value may vary, but something positive that we may consider. In next step, you just put the that is you just divide the entire formula by pi r by 3, and it became like this way. So here what you are doing, you are just taking this entire term into right hand side. The plus this thing you are taking it into the RHS, right hand side, right? So that's why from plus it is the same amount of positive is getting subtracted from the right hand side. In the next step, you just do the same thing. Okay, so but the something negative will be there, minus some positive, right? So Vs will be something like this. So the earlier formula minus something positive, which is less than this one, right? That means Vs is less than the Stokes law formula. Am I clear till this point? So for the Stokes law, as this plus thing was not there, which became minus at the right hand side. So that's why the Vs was equals to this thing. But in our case, Vs will be less than the Stokes law formula, the terminal Stirling velocity. Now we'll solve. So hope it is clear. Any doubt you can ask if you are not understanding in any step. Okay. So now we'll solve a problem based on this. So hope it is clear. This formula is very important formula. You have to remember. So it is Vs will be less than equals to Vp, where Vp is the Stokes law. Uh, Stokes law. Vp is the particle settling velocity as per this Stokes law. That's all. So now how we will solve a problem that we will see later. So now let's come to this problem. You have to find the terminal settling velocity, that is Ps millimeter per second of spherical particle with a diameter of 0.25 millimeters settling through water. Refer to the given data. So G specific gravity is given as 2.65. Small g, that is your gravitational acceleration, is given as 9.81 meter per second squared, and mu, that is your viscosity, is given as 10 to the minus 3 Newton seconds per meter square, 20 degrees centigrade. And rho W, that is the density of water, is given as 1000 kg per meter. Okay. So here accuracy, that is repeatability up to millimeter level before the decimal only. This much accuracy you have to consider. Stokes law region is not mentioned. You can see here. Okay, so that's why you have to do the iteration. So iteration means what? There will be a certain point where the iteration will be stopped. So there they are mentioning that where you will stop the iteration. You will stop the iteration at a certain level when the before the decimal. That means after the decimal, whatever will happening, you will not go up to that. Before the decimal, whenever the you see there is a match between two iterations, then you will just stop your iteration, and whatever Vs you have got at that time, at that point of time, you will take this as the answer. Okay. So this problem. I'll wait for you to calculate first the. I'll wait for 5 minutes for you to calculate the Vs based on the Stokes law region. First, you can assume the Stokes law. As I told you, that Stokes law is your starting point. As in this problem, Stokes law is not mentioned, but in this problem, REP is also not mentioned. That means your Reynolds number is also not mentioned in this point, right? So whatever you will get the Vs initially, from that you have to assume the REP. So in this way, you have to do a iteration. So first you do the calculation of Vs based on Stokes law. I will wait for 5 minutes, and you just tell me what the data you have got. So hope whatever you have discussed till now, it is clear. If any problem, you can ask. If no problem, you just solve this. You assume Stokes law, though in the problem it is not mentioned. But you see, in the problem, something is not mentioned, that how you will do the iteration. So that thing, it will be given in the question. So the formula that you will have to consider for do the iterations further, that will be given. Okay, so you can understand the Stokes law, right? I'll explain, but I hope till this point you are able to understand. Okay. So the data given are the mu value and the rho value is given. So that's why you can calculate the mu value, which is the kinematic viscosity or momentum diffusivity, which equals to the 10 to the minus 3 Newton second per meter square divided by 1000 kg per meter cube, which equals to 10 to the power minus 6 meter square per second. That is 1 micrometer square per second. Or millimeter whole square. Now G is given, that is the specific gravity 2.65. Small g, that is the gravitational acceleration, is given as 9.81 meter per second square. dp, the particle of the The diameter of the particle is given as 0.25 millimeter, that is this many meter. Now the detailed solution. The terminal settling velocity of ballasted, that is Stokes law particle, is given by, as I told you, that first you have to start your calculation of Vp using the Stokes law, which is nothing but G into G minus 1 into D square divided by 18 nu. Here was something as mu, so that mu actually we have taken below, so that's why mu by rho, sorry, there was rho in the numerator, that rho came into the denominator. So in this way it became nu, right? Okay, so now you just put the values of G, capital G, D square, etc., and 18 nu became something like this. So new value you just put here. Okay, and after calculation Vp became 0.0562 meter per second, that is 56.2 millimeter per second under Stokes law regime. So in this question it is not mentioned that you have to not mention that which regime it is following, but to understand in which regime it is following, you have to calculate the Reynolds number. For calculation of the Reynolds number, you require Vp. So after you calculate Vp, you have got nu, you have got dp, you can calculate rep, that is the Reynolds particles Reynolds number, and then you can consider get that is if the rep. So let's calculate, let's check the rep. So dp into what is that, vp, that is your this one. Okay, so the dp into vp divided by nu or dv rho by mu, okay, whatever new value you just put, and it came out to be 14.05. So if it was a one digit number from 1 to 9 or less than 1 even, fractions from 0 to 9 like that, so then you could have simply assumed that whatever value you got, this Vp equals to 56, this one, so whatever value you got using this Stokes law formula, you just equated this, right? So it was correct if the rep was approximately 1, around 1, but you can see that it is very greater than 1. It is why it is coming. Can you just interpret this using this 14.05 means what? If you just see the picture, the Reynolds number or rep is lying between, particles number is lying between 10 and 100. So it is coming in the transitional region. It is not in the laminar region, right? If it was less than 10, then it was in the laminar region. It is 10 or more, it is in the transition region for particles number, right? So that's why this Stokes law is not applied here. That means Vp is less than the value we have calculated earlier, 56.2 millimeter per second. Is it clear till now? So now you have to do, actually it is a very big number problem. 10 or 15 marks will be given if it is given in the exam. Let's conclude for today. uh, okay, so after solving this problem, I will conclude. Okay, so this is the last problem that I will be solving today. So if you are having doubt, you can ask. Okay. So then you have to do a iterative solution. How you will do the iterations, that we will be discussing now. So as the rep, that is the particle serial number, is a 2-digit number, we will solve it considering the transitional flow that I showed in the picture. We will follow an iterative procedure now to calculate the Vs, that is the terminal settling velocity. The procedure with which you will be calculating the iterative solution, if the Stokes law region is not given, then it will be given in the question. So you don't have to worry about that. So in the first iteration, as we saw, that it is a kind of tautology, right? You are asked that where is Ram's house? You tell it is beside the Sam's house. Now you ask where is the Sam house? You get the answer. It is beside Ram's house. So one is used as a reference for the other one, but the other one is dependent on the first one. That is the thing. So it's a kind of loop. So it's called as tautology. So iteration is something like that. You are getting VS, you are using that VS to calculate REP, and by determining by using REP, you are determining whether the value of VS, whether you have calculated it correct or not. That is the thing. So now the iterative procedure is something like this. So in our case, for transitional flow, we have to first calculate the drag coefficient. Drag coefficient is given by this formula. After solving this problem, we will be concluded. Okay. It is not working. What happened? Hmm. So drag coefficient is something like this. CD equals to 0.34 plus 1 plus 8 divided by root over of particles in number into 3 divided by root over of particles in number. This drag coefficients formula will be given in the question paper, which equals to, you just put the REP value in the formula, it becomes as 2.85. So next, based on the REP, you again calculate the VP. VP is your it is your particle settling velocity. This is a particle velocity. The VS will be less than VP. Okay, so which becomes, this formula is a bit different because it is a transitional flow. This formula will be given. It is not as per the Stokes law. It is given as, but the parameter that is using for the calculation of VP is almost same except the drag coefficient. So here it comes like something like this, because mu, that is the mu and rho, already taken care of in the REP, and drag coefficient is the function of REP. So that's why it is you be getting used here, and the other parameters are almost same. You can see small g, capital G, and small g. So which becomes as VP equals to 2 over small g into capital G minus 1 into D divided by 3C into this formula will also be given, equals to, you just put the drag coefficient that you calculated into this formula and the other parameters are known to you, you get this value. And you simplify, you get VP as 43.51. You can see it has come less than this one, 56.2. It has come less. But upon further checking REP, you get dp REP is formula is something dv rho by mu, that is dv by nu. You put the VP that you just calculated, not the earlier one. You calculated this one, right? You put that value here. dp is known divided by nu. Nu is also known. So dp, nu, and the other parameters are all known. Only the CD will change, REP will change, and VP will change. Again, based on this VP, you will calculate the next REP. After that, you will put this REP into the drag coefficient again. You will get again another drag coefficient. Then you again put that drag coefficient in the VP again, and again you get another VP value, and you have to compare this VP value with the earlier one. Here in the question it is mentioned that accuracy level before the decimal level. That means whenever the value, that is if you don't consider decimal, whenever the other value apart from the decimal will match, then that will be the answer. Okay, so this is the first iteration. So in the second iteration, you just utilize this again, this REP that you have just calculated, that you utilize this VP, you got this one you utilized, and again you calculate the drag coefficient using the earlier formula, something like this. CD equals to 0.34. The same thing will remain, only the REP value. Here you put the 14.0, but here you put the 10.88 that you just calculated. Okay, you got a drag coefficient new value, that is 3.456. Again you put this drag coefficient into the VP1. Okay, So you get another VP value. Okay. After checking from for REP, that is Reynolds number, you put that same VP value into there where DP and U are known. You get 9.878, and you can see that this VP you have got 39.512 is different from, than the earlier one. So the value you are getting before the decimal, that is different from the earlier one. So you are getting 39 now. In earlier one, you got VPS 43.51. But you can see the difference between 43 and 56 is more than the difference between 43 and 39. So that means the difference between VPs are getting lesser and lesser as you proceed through say, iterations. Okay. So now in the iteration 3, the REP value and VP value that you just calculated, that you have to use. Here you again use the same formula for drag coefficient, use the REP, get the drag coefficient value, put that drag coefficient value into the formula for VP for transitional flow, and you get the VP value as 38.1. Now you can see the difference between it was earlier as after equation iterations 2 it was 43, after iteration after iteration 1, after iteration 2 it is 39, and after iteration 3 it is 38. So from 43 to 39 to 38. So from 39 and 43 the difference is 4. From 39 to 38 it is difference is 1. So it is converging, right? So again you check the REP, and you put use that same REP for the next iteration. REP and same the VP that you calculated in iteration 3. So the REP and VP that you are calculating in earlier iterations, they are being used for your subsequent iteration. Is that clear? Okay. Just for the after solving this problem, we'll conclude. No worries. So you have to calculate the drag coefficient again. Again you calculate VP, and again you check Reynolds number. Okay. Here the VP you are getting, it is 37.525. You do iteration 5, and you get these VPs. Okay. So now whatever VP you have got, you can see the 37.3. This VP, there is not much change with the earlier VP, that is the iteration 4. After iteration 4, you got VP as 37.575. After iteration 5, you have got VP as 37.3. So you can see the portion of the value of the VP. There is a 37 that is before the decimal, because accuracy level they have told to consider before the decimal place only. So it has not changed. So then you can take the 37 as the final solution. Hence the answer is Vs equals to Vp. Here the Vs is not less than Vp now. It is 37 millimeter per second. So it is, yes, it is. You need a very difficult solution. So after that, okay. So we'll conclude now. So I will not discuss any further. So I mean, you just tell me one thing. You just unmute yourself. Only you are there. Nobody else is there. You just tell me freely that whether you have understood fully, whether you have understood partially, some doubt is there, or you not have understood anything at all. Just you tell. Just be free. No worries. So did you understood the iterative steps? As I told, the formula for drag coefficient, that is the CD, the formula for VP, that will be given to you. These two formulas you have to use for doing the iteration. At the first step, just use the Stokes law. You get the value of VP. Okay. Whatever value you have got, you just use that for calculating particles Reynolds number, that is REP, dP VP by nu. New value is given in the question. You just calculate the particles in a number. You check whether it is one digit Reynolds number or not. If it is not one digit, more than one digit, then it is the that is the last problem. Okay. Okay. So okay. So I will not discuss anything further. I'll just tell. You just see this one. See this one very carefully. Okay. See the earlier derivation. This was the problem we solved in our last class. We utilized this formula. All the data of the other parameters were given. We Stokes law was mentioned, that you consider it to be a Stokes law regime. You all the data are given. Vs is given. Everything is given. You just put all those values. You got the value of d. If the d is given, Vs is being asked. You can calculate the same thing and you can get the value of Vs. So it is for the Stokes law regime. Why? Because you can see this formula. This is the Stokes law formula that we derived today. Same formula. Vs equals to g into g minus 1 into d square divided by 18 mu. Mu by rho equals to nu. Okay. So if it is not a Stokes law, what will happen? So Stokes law, they will be equal in whenever they are not a Stokes law, then the value of Vs will be less than this Vp. Okay, so the entire thing is basically Vp. For Stokes law regime, they will be equal. For non-Stokes law, they will not be equal. If the questions they are mentioning it is Stokes law regime, use the equal formula. If in the questions they are mentioning it is not a Stokes law regime, then what you will do? You will start using Stokes law only. You will calculate the value of Vs equals to Vp. This one. So you will put all the data that is given in the question and you will calculate simply the value of Vp. That's what happened in this problem. We just calculated the value of Vp. But after calculating the value of Vp, so as I described in this picture, so how you will understand something is in Stokes law or not. So if it is they're telling in the question it is Stokes law, then it's okay. But it is if the Reynolds number is more very large than 1, that is in this region or in this region, that is more than uh, equals to 10 or even more than 100, then you will understand that it is not in Stokes law. Though you are starting the problem using Stokes law, but the REP value you are getting by putting the value of VP that you calculated using Stokes law formula, that is coming in this region. So that's why the formula that you used earlier, there is a delta term in it. So delta is not a specific value. Depending on which region it is, depending on in the transition region or in the turbulent region also, there are different formulas. So if the Reynolds number varies from this to this, you have to use this formula. Varies from this to this, you have to use this formula. So in this way, the iterative formulas changes. In our question, it is clearly mentioned, not clearly mentioned, actually it is given later, that you use this formula. That is drag coefficient formula, you use this one, and VP formula, you use this one. Using this formula, actually, you will start the iteration from VP equals to 56.2, which you calculated using Stokes law. After calculating, you put the value in the REP, you got REP to be more than 1. That means it is not in the Stokes law. That's why you have to go for iterations. And you are doing these iterations, iteration 1, iteration 2, iteration 3, iteration 4, and iteration 5. At the end of the iteration 5, you are seeing that whatever VP value you got in the end of iteration 4, the same value, almost same value of VP you are getting at the end of iteration 5. So that's why the VP value is not refining further. It is, yes, it is refining, but after the decimal level. And in the question, it is mentioned that take the accuracy up to up to before the decimal level on. So that's why you are not considering the refinement of the value of VP after the decimals places with further iteration. So that's why you are stopping the iteration at the iteration 5 only. So if you have done any coding means if you have done any coding, I don't know whether what background you are. So if you are from a BTech background, then you might have done coding, C programming or something in your first class, or in Fortran or Python or whatever. So there you'll see, I did actually C. So within C there is a concept of for loop. So within that for loop, you have to start that for loop with certain value. You have to end that for loop. You have to give a starting condition. You have to do a ending condition. So as we are writing iterations one after one after one, so there we will just define ending condition. You will write the function or program in such a way that it will end whenever the decimal value is not changing or it is same as the earlier. Are you getting? So the program will stop and at this iteration, and it will give you the value. So if you know programming, so you will be enjoying then this iterative kind of thing. So otherwise, in the exam, it is not like that you have to do all the iterations. They will just tell that you do just two iterations of three iterations. That's all. You just do one iteration, one or two iterations. They will be specifically mentioning that you do this on in the exam, or they may say that the accuracy level, they may say at a very large accuracy level they may keep. So even beyond millimeter level, so they may ask for accuracy level at centimeter level. That means one or two iterations you will get the result. So that's all. So in this way you are actually arriving at the final solution. So whenever the VP value is not changing significantly, the definition of significant will be given in the question. Okay. So then you are stopping at the iteration 5 and you are getting the VP value as this one. This is a transition state formula. The CD formula and the VP formula. So these two formulas, these are the iterative formulas. These will be given for transition state. For other states, there are other formulas. The Stokes law formula is a very simple one. So here the drag force is more than the Stokes law drag force. Okay, so that's why the VP is less than the Stokes law VP. Simple. Just it's a very cumbersome. So the problem is very lengthy, but the concept is very clear. Okay. Okay, so we'll wait for a couple of minutes. If there's nobody else is there, we'll be closing after a couple of minutes. So again, you can ask. You just unmute yourself and ask. You can ask me specific questions. So, what is that? What is that? Maybe you have not understood anything. Still, you can ask that. What is that line? It may so happen that to understand that line, I have to explain the entire thing, or maybe one or two lines back. So in this way, also you can ask. So no worries about that. Sometimes it may happen in our classes that professor is asking that in which portion you didn't understand. Just tell me you understand this or that which you didn't understand. But we don't have any specific question to ask because we didn't understand the entire thing. Whatever was talked from the beginning to the end, everything went above the. Yes, yes. When is the next class? Is definitely as usual. Is Tuesday from 7 to 9. Today actually almost half an hour actually we didn't discuss anything. Because participants is very less also, and it's a bit heavy today. I know, but always as I told that I am just a student, so that's why this is an interactive session. So this is for asking any doubt only. Whatever you are not understanding, you can directly ask. What is that value? Just remember, even if I discuss something, you can again ask that what is that, for understanding it and to grasp the essence of the problem. Okay, so after 1 minute, we'll be closing then. We'll meet in the next class at again the next Tuesday, 7 p.m. We'll meet. Otherwise, we'll end the session. Okay, fine. No doubt. We'll ending. We'll be ending. Bye bye.